Morning, everybody.
Morning.
Good morning.
Morning.
All right, folks, it's 8 o'clock. We'll get started here. We're going to be focusing on single order reactions today. I'll leave the chat box down here just in case anybody needs to put anything in there, and I'll try and keep an eye on it. If anybody puts something in there and I don't notice it, sometimes it falls behind other windows and stuff while I'm mucking around. So just let me know if there's something in chat that I need to address, and I'll address it. Okay, so we're looking here at single order reactions, and what I mean by that is we've just got one reactant going to products. Does it matter what those products are? Not particularly. Because what we're looking at here is the disappearance or the rate of disappearance of that specific reactant. A similar example, somebody's, Corey, would you mind muting, please? Or somebody needs to mute. Thank you. So what I'm talking about here is this is a similar situation. Would be down here. Let me see if I can find it. just looking for the stuff on initial rates that we had there. Here, there we go. So this is an example of a single reactant reaction, right? One that just has one reactant. It starts with C4H9Cl. And what we can look at here, if I could have people mute, please. Thank you. What we have here is a situation where this is disappearing. So how quickly it's disappearing will determine what order the reaction is going to be. And we can actually do some math here. It's a bit different to what we looked at earlier in order to figure out if we've got a zero, a first order, or a second order process. Now, when we're dealing with a single reactant, we can talk about what these zero, first order, and second order means in context of the kind of reaction we're dealing with. So I will go through each of those and show an example of each, and then you can get a glimpse into what the order of the reaction actually tells us. And I'll talk about the whole integration thing and everything else. It's a lot more simple than it looks at the present time. All right, so we've got our rate equation then. It's going to be Ka to the power of n, and n can be 0, 1, or 2, rarely 3 or more. Now, I'm going to give you a little bit of an idea about why the order is unlikely to be 3. If the order was 3, come on, I have to get my brushes here. Sorry about that. There we go. The kind of situation we'd be looking at would be this: A, and A. If the order was 3, what we're talking about here is a simultaneous collision of 3 molecules of A to form product. It's possible, but it's pretty rare. So we don't usually consider that kind of reaction order. Right? So the order can be construed as being the number of molecules involved in the slow step. And if there's only one step, then that's what we're talking about, is 3 molecules of A joining together simultaneously. So that's not really a very possible thing. So that's why we don't deal with that particular order very much for third order. We're only going to focus on 0, first, and second order as our examples here. So let's take a look. I'll come back to this in a minute. Here we go. So an example of a 0 order reaction. So if we're talking about 0 order, then the rate is equal to K, in this case, N2O4 to the power of 0. Anything to the power of 0 is 1. So the rate is simply K. And this is what's mind-blowing here. The rate does not depend at all on the concentration of the reactant. I'll say it again. The rate doesn't depend on the concentration of the reactant. That's what a 0 order means. That's the reality of it. Now that's incredible to me, that a rate could possibly not depend on the reactant. So the situation here is what's known as a catalytic reaction, or a metal surface reaction, I guess might be a better way of putting it. All right, let me get rid of that. Okay. So what we're talking about here is a situation where we've got a metal surface, and on that metal surface, we've got these little slots. And then we've got the N2O4 floating around above this metal. Now, there could be millions of N2O4 molecules floating around above that metal, but you'll notice there's only a very limited number of slots that these N2O4 molecules can enter in order to react. In the blurb here, I compare it to, I'm sure many of you have tried to find a parking spot at USF. It's hard. It's difficult. I've done it before. It's very difficult. You know, there's a lot of cars floating around, but only very limited numbers of spaces. And this is a similar thing. So what I'm saying is, whether there's 100 N2O4s, 1 million N2O4s, 1 billion N2O4s, it really won't matter, because the rate is determined by how quickly they can get into these very limited slots on the metal. So what that means is, in the end, the rate doesn't depend on the N2O4, which is why the rate is 0 order with respect to N2O4. Does anybody have any questions? Okay. So an example of a first order process. An example of first order process would be radioactive decay. And in the case of radioactive decay, the rate does depend on the concentration of the reactant, which makes sense because the more of some sort of radioactive compound we have or radioactive element we have, the more radioactive it's going to be. So a gram of U-238 is going to be going to be less radioactive than a kilogram of uranium-238. So that makes sense. So the rate here does depend upon the amount of uranium-238 we have to the power of 1. And a second order reaction would involve 2 molecules of a reactant. So we've got 2 NO2s, and this is going to make sense because if we look at what NO2 looks like, it'll be something like this. And it's got it's a single electron species on that nitrogen there. So these two things join together, which means there's 2 molecules involved in the one step, the single step, to produce this N2O4. Oh, sorry, is it's NO2? Yeah, that's right. So it might look something like that. But in any case, it's 2 molecules joining together to give the N2O4 molecule. And that's why the rate is going to be KNO2 squared. Now, the other concept we're going to be talking about here is half-life. Now, half-life, you've probably heard the term before, especially in relation to radioactive processes. The definition of half-life, I'll write it down over here on the board. The definition of half-life, I'll leave it up here, is the time taken to have half of what we started with. So in the case of some radioactive element, let's say uranium-238, for example, it would be the time required for us to have half of what we started with. And that's the thing, you know, that's the thing with radioactive elements. That's why they're so hard to get rid of, because it might take, say, even if it takes, say, even 20 years to have half of what you started with, then, you know, let's say you start off with 10 grams. It's 20 years to get to 5 grams, and then another 20 years to get to 2.5 grams, and then another 20 years to get to 1.25 grams. So you can see it takes a long time to get to a low amount of a radioactive substance, even with a relatively short half-life. Uranium-238 is like 10 to the 8th years or something. All right, does anybody have any questions? Okay. You all can hear me, right? I can. I am talking to you. You can see my screen and everybody's happy with that? Yes, good. Thank you, Georgiana.
Yes.
All right. Let's talk about the kinds of problems we're looking at here. Now, if you remember, well, I'll go back and show you the other kind of problem in a second, one we looked at the other day. But if you look at this one where we've just got a single reactant going to products, the data looks a little different to what it did when we were talking about the reactions that we did on last Thursday. And you'll see here that we're just given a time and a concentration of A. So as you can see, there's no real surprise here about what's going on. At time equals 0, we have a certain concentration of A. And then as time goes on, what happens to A? Well, it goes down. Why does it go down? Well, it's just because it's reacting. Now, how quickly it's going down in relation to the time will allow us to determine what the order of this reaction is. And what we're trying to determine is whether it's 0, first, or second order. All right, let me contrast that with the first one we talked about. You remember that it was 2 reactants and we were given an initial rate. So that's how it worked out. So we got 2 reactants and we got an initial rate. And that was a little bit different to what we're dealing with over here, which is just going to be time versus concentration here. All right, so let's see how we use this data in order to determine what order of reaction we're talking about. Well, to do that, we're going to have to do a little bit of math, but I'm not going to go into the math too deeply. This is a table that you'll be given with any test, and it's going to be invaluable to you when we're talking about trying to find the order of single reactant processes. So what I've got here are 0, first, and second order reactions, and these are the rate laws for that. So rate equals K, A to the 0, which is effectively K. For first order, rate equals K to be A, Ka to the 1, sorry, and then for second order, rate equals Ka to the 2. Right, so that's what we're looking at for the standard rates. Now these rates are very similar to what we call derivatives or differential equations. Now some of you might have seen these in calculus or other places. I'm not going to go into this, but it turns out that if you're talking about a rate, it's really change of something over change of something else. In this case, change of A over change in time. And I'm going to ask you to take my word on this, but in the case of each of these, they may be subjected to an operation called integration, which allows us to get rid of this derivative and come up with something that looks like a straight line, y equals mx plus b. So I'm not going to show you the in-between steps of that. I'm just going to ask you to take my word on the fact that if you've got Ka to the 0 here as the rate, that when you integrate it, you get A equals negative Kt plus A0. If it's first order, log A equals negative Kt plus natural log of A0. And for second order, 1 over A equals Kt plus 1 over A0. So you might be asking, well, what's this A0 business? Well, A0 is the initial concentration of A. It's a constant value. As you can see, each of these integrated rate laws does take the form y equals mx plus b, which is the equation for a straight line. So for 0 order, first order, and second order, we have 0, A equals negative Kt plus A0. So what we know is that A0, as I said, is a constant value. B is a constant value as well, if you remember your straight line equations. So we can sort of match what these things are. We've got Y is A, M is negative K, and X here is T. This is what's important. For first order, it's log of A equals negative Kt plus natural log of A0. And for second order, it's 1 over A equals Kt plus 1 over A0. Okay. So it's the same kind of deal for each of these. The Y value is what's on the left side of the equal sign, and the X value is time in each case. All right, does anybody have any questions so far? So what we can do in order to use this data that I talked about earlier, let's go back to that. And this is the data that we're talking about. What we can do is we can investigate what each of these graphs looks like. We can look at a graph of time versus A to see if it's 0 order, time versus log of A to see if it's first order, or time versus 1 over A to see if it is second order. And whichever one of those turns out to be a straight line, that's what order it happens to be, because each of these integrated rate laws takes the form of a straight line. So what that means is, and this would be the first step in this kind of situations, what you would do is you would have your time versus A, and then you'd extend out this graph here, extend out this table. And you'd look at log of A and then 1 over A in each instance. Now, to get this natural log of A, it's fairly simple. It would just be a matter of taking 5.00 and finding the natural log of it in your calculator. So I want you to take a look at that, make sure you understand how you might get ln of A out of A. So please look at that for now. And if you have any questions, now's the time to ask. Anybody have any questions about that?
So do you put ln of A into the formula and then you put the time as however it's changing?
Time will be X, and whatever is here is going to be the Y value, but I'll show you that in a second.
Okay.
But for now, I just want to see if people understand how to get natural log of A out of A. Is everybody okay with that?
Yeah.
Okay. So let's take a look at what I'm talking about here. Don't worry about the slope yet. I'll get back to that in a second. So if I drew a graph for time versus A, time versus natural log of A, and time versus 1 over A, using this as my data, so it's time and A, time and log of A, time and 1 over A, this is what I end up with. You can see that time versus A is a curvy graph like this. It's not a straight line. Same with time versus log of A, natural log of A. It is a curve as well. But if you look at time versus 1 over A, you can see that it is indeed a straight line. So since this one, the 1 over A, is a straight line, that means it's second order. Now, all of this comes from what I was talking about earlier with this table here. This is how I know. 0 order, Y equals A if it's a straight line. First order, Y is log of A. And for second order, Y is 1 over A. So whichever one happens to be a straight line, that's what links them together. And I've got it over here too. 0 first and second, what the Y values are on each of them. So whichever one happens to be a straight line, that's the one that ends up being the order. And that's how you can determine it. Does anybody have any questions? So, you know, obviously, most people aren't real fans of doing graphs in order to get this kind of answer. And that's because, you know, it's a bit time consuming to have to draw a graph for everything. So we're looking for a slightly easier way, perhaps, to figure out what the order of the reaction is. So one way we can do that is we can take the slopes of a couple of points. So what I'm talking about here is this situation. Let's say we've got a curved line like this. And I'm going to put some points on here. One way I can look at this and tell if it's a curve or not is to take the slope between, say, these 2 points here, the first and second point, and say the second to last and last point. If it turns out those slopes are different, I'll just redraw them over here, which they are. If the slopes are different, it means it's going to be a curve. But if you look at a straight line and you take the slopes of those points and they're the same, well, it must be a straight line. So that's what we're looking at here. So I'm going to sort of indulge you, ask you to indulge me for a little bit about, you know, how to find the slope of a line. This is something that hopefully you are aware of. It's going to be change in Y over change in X. It's going to be how we do the slope. So M equals rise over run, or the change in Y over the change in X. So for 0 order, this is what we're looking at. Let's go back here. I'll show you the data. So this is the data we're talking about. Here's the x. X is time. Y is a. So you can see the change in y over the change in x. So if we're looking at the slope between the first 2 points, it's going to be 5.00 minus 2.50 over 0.00 minus 80. That's how we're going to manage it. Does anybody have any questions to get a slope? All right, so that's what I've done over here. And you can see that the slope is negative 0.0313 if I do the math on that. Now, if I look at the slope between the last 2 points, this is what I get here. I get negative 0.00313. So they're not the same slope. And you can see if I go back to that, oops. You can see that the last 2 points are these 1.25 minus 1.00 over 240 minus 320. And that's how I'm getting that other slope. Now I know on the video, I think I might have, it doesn't really matter what 2 points you choose. And on the video, I think I chose different sets of points to what I'm going to show you here. But it's my belief that if something's curved, you'll get a better impression of whether it's curved by taking the first two slope, the points of the first two, slope of the first 2 points, and then the slope of the last 2 points. And that way, if there is a difference between them, you'll see it, and you'll definitely know it's a curve. If you take points that are fairly close together, or sets of points that are fairly close together, it's less apparent that it's curved. So it might be possible for you to mistake a curve for a straight line if they're close. So that would be my advice there, would be to do the first 2 points and the last 2 points. On the video, I think I did like the first 2 points and the first and last point or something like that, which still is okay, but it's more reliable to do it this way. Does anybody have any questions about what we're doing here? So we repeat the process for first order. You can see we end up getting, again, 2 different slopes. But for second order, you can see that when we take the slope of the first 2 points and the slope of the last 2 points, we end up getting the same slope, 0.00250 in each case. So again, to get that, it was this, this minus this, 0.2 minus 0.4 over 0.00 minus 80, or the other way around, it doesn't really matter. And down here, 0.8 minus 1 over 240 minus 320. And that's how we're getting the slope of the 1 over a. And it turns out that they're both the same. Does anybody have any questions? So that's how you can figure out if something's curved or sloped without doing a graph. I'll stop here for a second. Does anybody have any questions? Okay. Now you'll notice when I go back to what I've got here on the screen here in this area where I'm writing my chalkboard, you'll see that the x is always time. The m, which is the slope of the line, is actually k or negative k, depending upon which order we're talking about. Now, if you take a look at the graphs that I have here, you'll notice that the time versus a and the time versus log of a are both negative graphs. They have negative slopes on them, whereas this one has a positive slope on it. And that's always the way it's going to be. This one is always going to be negative, this one's going to be negative, and this one's going to be positive. And again, if you look at what we have over here, you'll see m is negative k, m is negative k. You'll notice this is slope, this is a negative slope, that's a negative slope. And then here, m is equal to k, which is positive, which matches this up here. The bottom line here is that the slope is the negative, k is the negative of the slope. K equals negative m, m equals negative k. It's the same thing. But the upshot of all of this is k will always be a positive value. K will always be positive because when the slope is negative, there's a negative in front of it anyway, which makes it positive. So k is always going to be a positive value, even when there's a negative slope. I hope that makes sense. So that makes this even more useful because now we actually have the slope. We found the slope here, which is 0.00250. That happens to be our k value. So m, actually here, I've got this here. Slope is negative k, so k equals negative slope. Slope is negative k, so k equals negative slope for 0 in first order. Then for second order, slope is simply k. So in this case, the slope is 0.00250, which means that k is 0.00250, and there's a unit here, molar to the negative 1, seconds to the negative 1. Now that unit is going to change depending upon what order we're talking about. Right, and it's going to be something that's going to have to be something that you can figure out on your own as well. So let's take a look at how we get the unit on those slopes. Does anybody have any questions so far? Anybody have any questions?
So finding the slope is just finding the time for k.
You have to, I'm not sure I understand your question, Alyssa. Could you?
So if you're finding the slope, you're just finding the time of k, so how it comes out negative for the first and the 0 order, but the second order is positive. That's just finding this.
It's the slope, not the time, Alyssa. The slope, that's what we're trying to find. And the slope is, change in y over change in x. That's how we're getting the slope. It's going to be whatever you've got on the y-axis over the time to get the slope. Is that okay? Alyssa, is that all right? Hello? Okay, I might have lost Alyssa. All right, so let's look at how we get the slopes units here for 0, first and second order. So I'll do it down here. And as I said, the unit will change depending upon which one we're looking at. So this will be 0, this will be first, this will be second. Now 0 order, if it's straight, will look like this. First order will look like this, and second will always look like that. So we've got negative slopes on 0 and first, and a positive slope on the second order graph. Now the unit, the y unit, is going to be, because it's a, for the 0 order, is going to be m. And the time unit, just for kicks, I'll make that seconds in each case. So t seconds in each case here. And for first order, it's going to be log of a, which actually isn't going to have a unit because you can't have the natural log of a unit, so there is no unit. No unit. That's on the y-axis. And on the x-axis, since it's 1 over a, on the y-axis for second, it's going to be 1 over m as being the unit. I'll make it a little bit clearer. There we go, it's better. So we've got 1 over a is 1 over m. So when we take the slope, which I've got the equation over here, you can see how we might come up with the different units. So the unit for the slope in the 0 order is going to be, let's see where I'm going to put this. I'll do it down here, molar per second. Actually, I'll do it somewhere else. So the slope unit for zero order is going to be molar per second. For first order, it's going to be per second. And for second order, it's going to be 1 over ms. So what I'm talking about here is just doing the y unit over the x unit. The x unit is always going to be seconds. So the first one, zero order, is going to be molar per second. First order is going to be just per seconds, or 1 over seconds, if you will. And the 1 over A for the second order is going to be 1 over ms in order to get that unit. Does anybody have any questions?
I do. Why are the units different?
Because the y units are different in each case, and we're finding the slope, which is always changing y over changing x. So the unit for the rate will change as well, because the unit for y is changing. That's the reason.
Okay, thanks.
All right, any other questions? Okay, I'll show you what a test question looks like, at least on a real test, what it would look like on a real test, and then I'll show you how it looks on the test you'll be taking, of course. Let's have a squiz. Okay. So you can see that for a problem like this on a pen and paper test, that's the initial problem there, reaction time versus A. And then we find natural log of A and 1 over A, just like I showed you, extending that out. And then finding the slopes of each by taking 2 points. In this case, I think the student took the first 2 and last 2 points on each one. Tried to figure out which of these had something where the slopes were close together. And it turned out that for zero order was negative 3.5 times 10 to the negative 4 versus negative 4.2 times 10 to the negative 5. So those were fairly far apart. In the case of first order, 0.0046 versus 0.00148. And for the case of second order, 0.062 and 0.0599. So that was fairly close together, which meant that out of those three, it's most likely second order. Any questions about how this one was determined to be second order? Okay. So what happened then was they found, well, that is the slope. Now, I know there's 2 different values here. You've got a couple of options. You can just use one or other of them. It doesn't matter which, or you can find the average of them. The reason they're not exactly the same is because it's not a completely straight line. There's always going to be a little bit of variation, a little bit of error. So that's why it doesn't really matter what you take as far as the slope goes, as long as it's pretty close to what you figured out. So the K was slope 0.062, and the unit there is 1 over ms, as I talked about earlier. The last thing we need to find here is the half-life. And to do that, let's go back. It's not that difficult. To find the half-life, I actually have all of the half-life equations in this table. Remember, you have this table. You don't have to memorize these. And half-life calculations are different depending upon which order we're dealing with. So T half, that's the half-life. In the case of zero order, it's A0 over 2K. For half-life of first order, it's 0.693, which is the natural log of 2 over K. And for second order, the half-life is 1 over A0 times K. So if we know that we've got a second order process, then that's going to be the equation we'd use. If you remember what A0 is the initial concentration of A, which we can get from the table. So in this case, it's 0.950. The K value we've already got as well, 0.062. You can see the units cancel, and we'd be left with time here. So just to give you a little bit of context as to what half-life means, if we start with 0.0950, the time for the half-life would be the time to get to half of that. Now, half of that would be about, well, it's pretty close to 0.05. So it'd be a little bit less than this here, a little bit less than 0.05. You'll notice to get to 0.05, it'd be 150 seconds. You'll notice to get to a little bit less than that, it's 170. So it kind of makes sense that we can eyeball an estimate at least of the half-life by looking at what half the starting material would be and comparing that to the time. So that would be 170 seconds in this instance. Does anybody have any questions? All right, let's go take a look at the kinds of things that you'll have to investigate here. So I'll go back to, whoops, not press this one. I don't think I pointed this out. I will point it out now though. But every single one of these practice test questions, this ungraded copy of test 1, every single question has a video for it on how to do it. So even if you're not really sure about how to do something, you can always watch these videos. They don't give a whole lot of background information, but they do show you how to do those specific problems. The background information is more in these mini lectures here and of course in the information I'm giving you today. All right, let's take a look at the kinds of questions we're looking at here. Oops. I need to preview that. There we go. All right, so question 2, reaction orders of single reactants, and these are all the questions associated with that. So all the way down from, let's see, what is it? From question 5 down to question 11. Right, so all of those relate to what we just talked about. It's just split into this number of questions. I think it's like 7 questions. All right, so let's take a look at each of these. So the first one, question 5, what you're looking at is reaction time in seconds and then these concentrations here. And your mission here is to figure out which order it is, and it's just multiple choice. Is it 0, first, or second? So how do you do that? You start off by doing this. You find the log of A, you find 1 over A for each of these, and then you do the slopes of the first point and second point and the third point and fourth point. So the first 2 and the last 2. Find the slopes, see which one has the same slopes. That's a straight line. It could be any of those 3. Does anybody have any questions about how to do number 5 here? Okay, I'll come back to this and I'll go through it in detail, but that's not really the one I want to focus on. I want to focus on some of these other ones because they're a little bit less intuitive. Yeah, keep in mind that anything you put in the chat here is something that I'll see, and unfortunately everybody else will see it as well because I have to have the chat up. All right, let's have a look. Now let's look at this one, number 6. The partial data table is from a reaction found to be 0 order. So I'm telling you the order here, and now I'm asking you to calculate K. So what do you have to do with that? Okay. Well, let's see. Okay, I guess I will do this first one here because it is kind of germane to what I'm talking about here. All right. I need to find my thing again here. So this will be good practice for all of us here. So let's see. We've got our reaction time. And that's in seconds. So RT in seconds. So we've got 0.000, 28.16, and 61.75, and 88.92. And then we've got our concentration of A here, which is of course in molar. And that's going to be 0.541 and 0.329 and 0.223 and 0.178. Next thing we're going to do, and I'll do this over here, we'll have ln of A, and that's not going to have a unit because you can't find the natural log of a unit. And then in this box here, we'll have 1 over A. And the unit there would end up being 1 over M, as we talked about earlier. All right, so what I'd like you to do is I'd like somebody to call out the natural log of each of those that we're doing here. You all should try it, but I just need somebody to tell me what the values are for ln of A.
All right, the first one is negative 0.61.
Let's go for 3 sig figs, Kyle, if you don't mind.
Okay, negative 0.614.
Okay.
Second one is negative 1.11. Natural log of 0.223 is negative 1.50. And the last one is negative 1.73.
Okay. All right, let's look at 1 over A.
Okay, I already did those two. The first one is 1.85.
Okay.
3.04.
Mm-hmm.
4.48.
4.48.
Correct. And then I haven't done the last one. That's right. 0.178. 5.62.
Okay. All right, so looking at that data, how we've got the log of A, the 1 over A, does anybody have any questions about getting any of those values? Does anybody have any questions about getting any of those values? All right, that's good. That's good. So let's look at getting some slopes here. Well, actually, why don't you all try it? I'll just do a couple here just to put you on the right path. But we'll do A versus time here. So A and time, or time versus, well, yeah. We'll do A and time here. And what I would do is I think that's 0.329. Okay, I do 0.541 minus 0.329 divided by, see that's Y, that's the X. I do 0.541 over minus 0.329 over 0.00. It's got to match, you see, minus 28.16. And then I would do 0.223 minus 0.178 over 61.75 minus 88.92. So I do both of those and see where I what I came up with on each of those. So if somebody would tell me what they get for that, and then I'll put them in just for the first one. And then what I'm going to get you to do is I want you to do the same thing for ln of a and 1 over a. If this one doesn't turn out to be zero order, it's going to be lucky if it is. I don't know if it will or not. We'll see how close these two are. I can't tell by looking at it.
The first one is negative 0.0075.
Okay. 0.0075 negative?
Negative, yep.
Okay. And the other one?
For the other one, I got negative 0.0017.
Okay, I don't think it's zero order. Okay, those two values are not very close together. All right, so let's take a. I'm not going to do the rest of these myself. I'd like you to investigate this, see if you can come up with what order it is. I'm just giving you the hint. It's not zero order. So I'll give you a couple of minutes to see if you can figure out which order it happens to be. And when someone comes up with the solution, I'll write down what the slopes are for each one, and then we'll take a look at it. Okay, does anybody have an answer yet? Can't be zero order. Is it first or second?
I got second order.
Yeah, second order. Could you tell me what slopes you got, please, for the first and second points, and the second and last and second to last point? Just
For the first and second point, I got 0.0423, and for the last 2 points, I got 0.0420.
Okay, 0.0423, 0.04. Is that right? 0.0423 and 0.0420? Is that what you got?
That's what I got.
Okay. Can anybody else confirm that?
Can you, I know how to do the math, but can you just go over how to set up the first order and the second order slopes to make sure that I was putting in the right numbers?
I'll do the first one here for the 0.0423, okay?
Okay.
So that would be I'm going to switch it around here. 3.04 minus 1.85 over 28.16 minus 0.00. Is that okay?
Yes.
So what was done here? I'm not sure. I'm not sure who gave me the answer there. I'm sorry about that. And the second one, we would use that data, and that should give 0.0420. Does anybody have any questions? Did anybody come up with values for the first order for the log? Did anybody actually? If you could just say them, and I won't write them down, but just so we can see that they were different.
For the first order slopes,
Yes.
for the first one, for the first 2 points, the one I got was negative 0.0176.
Okay.
And then for the last 2 points, I got negative 0.00847.
Yeah, so big difference between those two. So we know it's not first order, we know it's not zero order. And then when we look at the second order, we can see that it's 0.0423 versus 0.0420. So that's how we know it's going to be second order. Does anybody have any questions about this?
Yes, sorry, just really quick.
Yeah,
so
that's
what
all right.
were the numbers you plugged in to set up the slope for first order? I understood zero order and second order, but for first order, how would you set that one up?
Okay, so I'll just do these two slopes here, right? So these 2 points here, and it would be negative 1.11 minus negative 0.614 over 28.16 minus 0.00. So that would be for this.
Okay, I got it. Thank you.
Is that all right?
Yes.
Okay. Does anybody have any other questions about this? All right, so because these two slopes were close together, I'm going to say second. Right, that's as simple as that. That's what I would do for that. Okay, any other questions? Okay. All right, let's look at this next one here, and you'll notice that what it is you're given a partial data table. And what you're looking for, you're told that the slope is zero order, so you're looking for the value of k. So remember that k is going to be the slope, but if it's zero order, then we're looking at time versus a, which means that really all we have to do here is find the slope of these two right here. Now I'm going to go back to that, and oh, I didn't mean that. Hang on, I will just cut out some of this here. Okay. So for this question, which is looking for the k value, you remember that the slope, if it was zero order, the slope would be based on a versus t, or a versus time. So for this one, it's really just a matter of doing 4.67 minus 1.20 over 18 minus 102. All right, can somebody give me an answer for that, please?
I got negative 0.04.
Okay, well, can we let's do two sig figs on that. Another
0.041.
Okay, so negative 0.041, right? I'll put a 0 here. You don't have to put the 0 in front, but it'd be negative 0.041. The units on this, because it's zero order is going to be molar per second. Now, the reason I know that, again, is because it's A versus time, so it's molar per second. And we're told in the problem that zero order. That's how I know it's zero order, because it says so. So it'd be M over S would be right down here as the unit. And both of those, you know, there's partial credit given here for the unit as well, so make sure you get that right. Does anybody have any questions about finding the value of K given this partial data table here?
Wouldn't K be positive because K equals this?
Oh, you know what? Yes, thank you. I knew that. I was just testing you to make sure that you were paying attention. But yeah, you're right. The slope was negative. So yeah, let's go back and take a look at that. Thank you for pointing that out. Yeah, so for zero order, you can see that the slope is negative K, which means K ends up being a positive value. Thank you very much for that. Yeah, so K equals negative M. All right, any questions about that? All right, so for this one here, again, a partial data table, but we're told this time it's first order. Can anybody tell me the strategy we'd have to undertake for this one? I give you a hint. It's a little different to what we did in the previous question. Does anybody want to reveal what their strategy would be for this question?
Start by finding the natural log of A.
Oh yeah, that's what I would do. Let's do it. So I mean, I'll just show you the rough working here. You all can see how it works out. So it'll be ln of 5.14 minus ln of 1.77 over, making sure I get this right, 52 minus 102, yeah. And that gives us a value. Now this is going to be, in this case, it's going to select that. Okay. It'll be ln of A, oops. Okay. All right, what do we get there on that one?
I think it's a negative 0.021.
Okay.
But then it would be positive 0.021.
And that's right. And the unit there would be, because there's no unit on natural log of a concentration, it'll be 1 over S would be the unit. So that's right down there, 1/S. I suppose /S would be correct as well, but I don't know if I've got that. I think I've got 1/S as the unit there as the answer. Does anybody have any questions? Sorry. Anybody have any questions about that one? So again, the sign of that, you'll see that M is negative K. So the K is the negative slope, which makes the K positive, which is why this is positive 0.021. Any questions?
Would the significant figures be important?
Well, not for this really, because I have a tolerance on the answers, Theodora.
Okay.
So, you know, I mean, if you get something that's close and you're finding it's been marked incorrect, let me know. Maybe my tolerance isn't enough, but I think I've put a decent tolerance on each of these, something like 2%. So 2% either side of the answer, it should work out. So the significant figures here, I'm not really looking at sig figs too hard on this specific problem, because it's more about, well, anyway, it won't matter. It's the bottom line.
Okay.
All right, what about question 8? What would be the strategy that you would undertake here? Okay, any ideas? What would you do for this one, for number 8? Oh, sorry. Second order. You've got to see the question here. Second order. So what would you do here with this one? Any ideas?
You would do 1 over A.
Yeah, let's do it. Ugh. So it would be 1 over 6.03 minus 1 over 1.98. Sorry, yes, 1.98. Over 54 minus 102. And that would give us our answer there. Now the unit here, this is 1 over A. So the unit would be 1 over m on the y-axis. All right, so could someone tell me what the answer would be over here for number 8? Oops.
.0071.
And that was positive anyway, and then it'd be 1/ms. That would be your unit. All right, does anybody have any questions about any of those? I want to point out something. You do have this table here. Don't worry about this down here. This is just an accessible version for a screen reader. Just look at this one here, and you can see you don't have to memorize anything because you've got A, you've got log of A, and you've got 1 over A, and that links each of the 0, first, and second order to whatever the Y value is going to be for each of those. So there's no memory here because it's all here in this table. Okay, let's have a look. Question 9. The partial data from this reaction is found to be 0 order. What's the half-life? So what you'll do is you'll go back up to the table here, and you'll look at the half-life equation here. All right, there it is. T half is A0 over 2K. So the strategy that you would undertake here to answer this question is, let's see, what did I say? It's T half equals A0 over 2K, I think it was. Now, A0 is going to be 6.95. That's the concentration. That's the concentration at time equals 0. And then you do 2K, and K is going to be the slope in this case. So slope is equal to K, negative K. Slope is equal to negative K. Or K is equal to negative slope, let's say. So the idea would be we just do exactly what we did previously back in this question, question 7, or question 6, I should say, where we had a 0 order reaction and we found the slope between these two without changing anything because that's all we needed. But over here for number 9, when we're looking for the half-life, then what we're going to do is plug in the equation here, plug in the 6.95, and then just find the slope in the same way. I'm not going to do that again because we already did that. Does anybody have any questions about finding that half-life? Now, the unit for half-life is always going to be whatever time unit you're given here, so it'll be seconds in this instance. And that'll be the same for all the half-lives as far as that goes. For number 10, the partial data table is from reaction found to be first order. What's the half-life? Well, in that case, the half-life is 0.693 over K, and then you just find, well, this one doesn't even depend on the initial concentration of A, so you just need to find K, which is going to have, again, be the negative slope. But it's the slope of the log of A versus time. Just like we did back in question 7. Yeah. Does anybody have any questions about number 10 there? Again, the unit's going to be seconds. The last one here is going to be, well, same kind of deal. See, T half equals 1 over A0 times K. So A0 in this instance would be 5.32 molar. So that's the concentration time equals 0. And K is going to K equals the slope. But it's the slope of the 1 over A versus time. And that will be how you'll do that one. Just like we did back in question 9, I think. No, question 8. All right, does anybody have any questions about any of those? Anybody have any questions?
Yeah, I have one.
Yeah.
So on the calculator, when you get K and it's a negative, and in the formula it's a negative, that makes it a positive?
That's right.
Okay.
Yeah, because of the table up here, if it's a negative slope, it means that you want to take the negative of that to get the positive value of K.
Okay.
In each case.
Makes sense.
Okay. Does anybody else have any questions? See, once you know how to do this stuff, it's not really that difficult. Then it just comes down to practice. And you've got plenty of stuff to practice with here. You can just do this test again and again and again and again until you're getting it. If you keep on getting the wrong answers, it means that you must be doing something wrong, so you get help. That's the idea. Does anybody have any questions?
When I set it up in the calculator, should I just do the top problem first and then divide it by the bottom number? Like click equal and then divide it by the bottom number?
Yeah, or use parentheses, possibly.
Okay.
Yeah. Yes, Marissa, I think it's a smart play. Just videos and repetition. I mean, look, if you're getting it right here, how can you get it wrong on the test if it's the same questions? That's what I want to know. That's what I say. All right. Anything else? That's all I wanted to cover today. I just wanted to get through the single reactant orders today. That was it. Anybody got any other questions about this? Well, you've got plenty to work on. You've got, as I said, this ungraded copy. If it was me, I'd just do the problems, let's see, 5 through 11, again and again and again and again until I was getting the right answers. And if I was getting the right answers, then I think I'd be feeling pretty good about myself, is how I would do it. And then, for an extra bit of fun, you've always got the fun quizzes here. You've always got the fun quizzes. Let's have a look. It would be under reaction orders for single reactants. and you can do that practice quiz and then the credit quiz a couple of times and get yourself some bonus points. Same kinds of questions. They're a little bit more challenging, I will admit, but you know, I think you'll be all right. All right, does anybody have any questions? Anything at all? All right, well, I'll leave it there for today, and I'll see you all on Thursday. Anybody who wants to hang around and ask some questions, you're more than welcome to. For everybody else who's in my lab, I'll see you in lab. If not, I'll see you Thursday.
Thank you.
Thank you.
Yeah,
Thank you.
Okay, Mariam, Victoria, do either of you have any questions? All right, I'm going to assume that you're not at your computers presently. Oh, no, Mariam says thank you. Okay, good. Victoria, do you have anything? Okay, thank you.